Professor Peter Moffatt, right, from University of East Anglia. Right? Professor Moffatt is a professor of econometrics. His principal research area is experimetrics. Is the econometrics analysis of data from economic experiments. He is the author of textbook Experimetrics. He is particularly interested in the models that allow for between subject heterogeneity, right? So it's something linked with the phenomenon of experimental subjects differing from one another in dimensions such as risk aversion, selfishness, and cognitive ability. Right? He has worked in a number of other areas of economics and econometrics, including the modeling of household debt and the theory of the consumer. Right now, he is currently working on a project in which supermarket scanner data is being used to predict the impact of the sugar tax. Tax on sugary drinks that will be introduced in the UK. Yeah. So we also have some kind of sugar tax here as well.
Really?
Yeah.
I might talk to you about that afterwards.
Okay. Yeah. So let's welcome Professor Moffatt.
Okay. Thank you for that great introduction, and thanks for the invitation. It's very nice to be here. I'm talking about behavioural economics. Theory and practice. Now, when I say practice, I mean how to test behavioural economic theories using real data. In other words, how to use econometrics to test behavioural economic theories. And there's a name for that, and that is experimetrics. I hope you all know this word, experimetrics. The econometric analysis of experimental data, experimetrics. That's my speciality. And yes, I'm from the University of East Anglia, which is in Norwich in the UK. Well, I mean, this is where it all started. Who is this person? Sorry, I'm asking the audience a question. Who is this person? As a youngish person and as an older person. The same person, who is it? Are you shy? Well, okay. There was a Hollywood movie called A Beautiful Mind, starring Russell Crowe. And I think this person's a bit better looking than the real John Nash, isn't he? But anyway, the Nash equilibrium was named after John Nash, the mathematician. He was a mathematician, but he won the Nobel Prize for Economics in, I can't remember which year, early 2000s. And these are the publications, these are the key publications, okay, in which the Nash equilibrium concept was developed. That was the starting point, the Nash equilibrium. How do we predict people to behave in an interactive situation, given certain assumptions, given the assumption of perfect knowledge, perfect rationality, self-interest, given all these assumptions, how do people behave? Well, that's very useful, but it's not useful in practice, because in most situations, if you put people in a laboratory and you get them playing games with each other, they do not behave according to the Nash equilibrium. They behave according to something different. And that's why we're interested in behavioural economics. Behavioural economics is why and how do we depart from the theoretical predictions. Agents depart from neoclassical assumptions of rationality and self-interest. Why? What are the reasons for this? They do not have complete information. That's obvious. We know a certain amount, but we don't know everything when we're making decisions. We do not have immaculate powers of reasoning. We do not have the computational skills that require us to work out the optimal decision in a given situation. We cannot correctly predict the behavior of others. This is another assumption that's made. You have to be able to predict what other people are going to do. And maybe we get that wrong. And fourth, probably most importantly, we don't just care about ourselves, we care about other people as well. So these are all reasons why we depart from neoclassical assumptions. And these are the reasons why behavioural economics has become so important, such an important part of economics. And if you know what behavioural economics is, you'll know it's sort of halfway between economics and psychology. They're interested in how the brain actually functions. Behavioural economics is concerned with why and how agents depart from rational self-interest. Okay, and experiments have been very useful. Experiments have been probably the most important part of behavioural economics, but they're not everything. I mean, there's theory in behavioural economics. There's also field data. We don't just use experimental data from the lab, we use field data as well, we use naturally occurring data, so it isn't always experimental economics. There's a strong link between these two things, behavioural economics and experimental economics, but experiments aren't everything. Okay, now the dictator game is the context that I'm using for this presentation. The dictator game is very simple. The dictator game has two players, A and B. A is the dictator and B is the receiver. Player A has the task of dividing some fixed endowment, $100 say, between themselves and player B. Player A's decision takes the form, I get $90, you get $10. Player A is the dictator, player B is the receiver. The role of player B is entirely passive. Okay, so player B doesn't actually do anything. The decision is the only decision is made by player A. Now, why is this such an important game? You might think it's, if you've never seen this before, if you haven't got much experience in experimental economics, you might think this is a bit silly. Why play such a trivial game? Why are we interested in it? It's because it's a way of testing a very basic assumption that we make when we do economics. Observed behaviour in this game allows a very straightforward test of the homo economicus model of individual behaviour. If individuals were only concerned with their own economic well-being, player A would allocate the entire amount to themselves and transfer 0 to player B. That's it. In game theoretic terms, 0 giving is the Nash equilibrium prediction. Okay? That's what we predict in theory using neoclassical economics. We predict the dictator to keep everything for themselves and give 0 to player B. When we do this in a lab, there is a vast amount of experimental evidence to reject this model. I don't know what's written here. Dictators give about 20% of the endowment to the receiver, on average. That's what it says. On average, dictators give 20% of the endowment to the receiver. Some dictators give much more than that. Some give 50%. Some maybe even give it more than 50%. But some also give 0. So there's a lot of variation in behaviour, but the average of behaviour is definitely positive giving. This statistic, 20%, is in the textbook by Colin Camera. That's 2003. That's a very, very good book by Camera, Behavioural Game Theory. Now, why do agents give when they're in the role of dictator? Why do we not observe the Nash prediction of 0 giving? Well, there are a number of possible reasons. Altruism is probably the most obvious. Altruism is you care about other people. You do not just care about yourself. You want other people to have something as well. Now, that's altruism, caring about other people. And there's an interesting, the second reason is more subtle. You care about yourself. Obviously, you care about yourself. But there's a way in which you can give to other people in order to satisfy yourself. And that is called warm glow. That's what we call warm glow in behavioural economics. That's if you're giving and you get pleasure out of giving. So it's a sort of selfish reason for giving. and it's called warm glow. There's a third reason for giving it a dictator game, which is the experimental demand effect. Now, this is when you're an experimental subject, what goes through your head. If you're in a game like this, you're in a lab, you sit down, and someone says to you, this experiment is about giving. In this experiment, we are testing the hypothesis that people are selfish. We're interested to know whether people are altruistic. So that's what you're told at the beginning. So what do? Do you act selfishly, or do you want to demonstrate that you're altruistic or whatever? This is called the experimental demand effect. That subjects in experiments, there's a sense that they are doing what the experimenter expects them to do. And obviously that's not what's intended, but it's something we need to take account of when we look at experimental data. So, is it possible to increase or decrease giving by manipulating the experimental conditions? We know that people give. What becomes the interesting question is when you change the experimental conditions, do people give more or give less? That's what we've become interested in behavioural economics. Now, there's a very useful meta-analysis of dictator game experiments. The meta-analysis is performed by Christoph Engel, and it's published in Experimental Economics in 2011. A meta-analysis is an econometric analysis of lots of published studies. So what Engel did is he took all the dictator games that had ever been done, 300 dictator games, and he put them all in a spreadsheet, a data set, and he recorded the characteristics of each dictator game. So all dictator games have slightly different experimental designs. So he looked at the characteristics of all the different experiments, and using regression analysis, he found what characteristics of the dictator game cause subjects to give more or give less. And you won't be able to see this very clearly, but this is a copy of a graph that is in this meta-analysis article by Engel, and it basically shows the features that tend to increase giving, the features of an experiment that increase giving, and the features of an experiment that decrease giving. Now, as I say, you won't be able to read this, but the interesting ones are multiple recipients. If you're giving to more than one person, then you tend to give more. Recipient earned. Now what that means is if the recipient, that is if player B, has earned the endowment, then you want to give more to them. The endowment has been earned by player B, then you want to give more to them because they earned the endowment. Deserving recipient. Deserving recipient means that you're not giving to another subject, another student subject, you're giving to a homeless person or someone who is in need of money. If the recipient is deserving, there's a tendency to give more. If it's a group decision, these are things that cause you to give less. If it's a group decision, that means if the dictator is a team, if the dictator is maybe a team of 3 people, then there's a tendency to give less than if the dictator is a single person. If it's a repeated game, that is if you play dictator games over and over again, you give less. What else is interesting here? What's the biggest negative? The biggest negative is dictator earned. And what that means is if the dictator has earned the endowment themselves, then they're much less likely to give. They'll give much less. I think that's the really important one. Basically, this is the type of experiment where the first stage of the experiment is subjects earning money. You're doing a task and you're earning money, and then you've got some money, and then you're asked the question, how much of this money do you want to give away to another person? Well, if you've earned that money, you're less likely to give it away. If it's what's called manna from heaven or house money, if someone just gives you some money and then says, how much of this money do you want to give away, you're willing to give it away. But if you've earned it, you're less likely to give it away. Now, I think that's an important one because in real life, the money that we carry around is usually earned by us. So that's why we don't go around giving our money away. The reason why we don't give money away in real life is because it's earned money. So this was a very useful meta-analysis for finding out, for discovering which features of an experiment increase and decrease giving. What we're going to do here is look at some data. I'm going to look at a particular data set with a particular treatment. This is how experiments are done. You focus on one particular treatment and you test the effect of that treatment. The treatment that I'm looking at is communication. So what we've got here is we've got a dictator game and we've got 30 subjects in the no communication treatment and we've got 30 subjects in the communication treatment. What does communication mean? Communication just means the recipient sends a message to the dictator. And it might be a message on a piece of paper or it might be a message on a screen, on a computer. And it's just to say, look, I'm a real person. I'm like you. I've given up my time to be here. I'd really like to get some money out of this. Please, can you give me some money? Or something like that. Some sort of message passes from the recipient to the dictator before the dictator's decision. So we've got 30 subjects who have the communication, and we have 30 subjects who do not. That's 30 dictators who have no communication. We have 30 dictators who have communication. So the total number of subjects in this experiment is how many? We've got 60 dictators and we have to have 60 recipients as well. So the total number of subjects has to be 120. Okay, now we've got some data from this experiment. This is the distribution of the 30 dictator decisions with no communication here. This is the distribution of the 30 dictator decisions with communication. Now I think we can see that there's a shift to the right. Communication causes a shift to the right in the distribution. In other words, communication increases giving. See, with no communication we've got a lot of zeros. With communication we've got fewer zeros and we've got more 50s. With communication we've got more, these are called equal splitters. People who split the pie equally are called equal splitters. With communication there are more equal splitters than with no communication. Notice that with communication there are some observations above 50. So the communication really has had an effect there because people are giving more than half of the endowment. They must have been really interesting messages. Anyway, there seems to be evidence here that there's a shift to the right in the distribution. The question is, how do we test this formally? What test do you use? If you were going to test, do a formal statistical test to answer the question, is giving higher with communication than with no communication? What test would you use? Again, I'm asking the audience a question here. A what? T-test, that's right. Does everyone know what a t-test is? A t-test, a t-test is usually used in regression. When you do econometrics, you have a regression slope, and you want to know if the slope's significantly different from zero. That's in regression. But an easier version of the t-test is when you're just comparing two means. See, we've got a mean here, and we've got a mean here. The mean here is about 40, and the mean here is about 20. And the question is that 20 significantly larger than the 40? Is the difference significant? We answer that using a t-test. Okay, the t-test statistic is the difference between the two sample means, so it's 20 minus 14 divided by something complicated which turns it into a t-statistic. And then we just compare that with tables and we get a p-value and so on. Now the thing is, when you do a t-test, what are you assuming about the data? What are you assuming about the distribution of the data when you do a t-test? You're assuming the data is normally distributed, roughly speaking. If the sample's very large, you don't have to worry so much about this. But with samples of this size, we have to worry. Is this data normally distributed? No, it's not, because look, we've got a whole lot there. By the way, these little curves here are curves of the normal distribution with the same mean and variance as the data. So putting the normal curve there verifies that this data is not normal. And it's not normal mainly because you've got a huge mode there at 0, you've got a huge mode, well, there at 50 anyway. So it's not normally distributed. So there are strong reasons for maybe not depending on the t-test, because the t-test assumes normally distributed data. Okay, well, I think this was mentioned at the beginning when I was introduced. This is a textbook by me called Experimetrics, okay, and it was published in 2015 by Palgrave Macmillan. And one of the chapters, one of the early chapters of this book is a chapter on treatment testing. So all the treatment tests that I'm going to talk about in the next few minutes are in an early chapter of this book. We said the t-test is an obvious test. The t-test compares two means. But let's say you're just interested in whether people give. How do you just look at the decision to give? Here we're talking about giving as a binary. Okay, you either give a positive amount or you give 0. Give a positive amount or give 0. See? 0, 1. Positive, 0. The treatment, no communication, communication. This is what we call a cross-tabulation. This is the statter command that gives this. This is the statter command, tab. Does everyone here use statter? Yes, you use statter in teaching. Good, please. Are you on version 16? Versions?
We right now using version 15.
Get on to 16 as soon as you can, because there are big advantages with version 16. Okay, what we're seeing here is we're seeing in no communication, we're seeing 21 out of 30 giving. 21 out of 30 give with no communication. With communication, 26 out of 30 give. That seems to be quite a difference, but is it significant? How do we know if this difference is significant? What tests do we do? Chi-squared test. Chi-squared test is basically a test. Is the 21 out of 30 significantly different from the 26 out of 30? That's a chi-squared test. Very easy to do in Statter. You just add that after the comma. And we get a chi-squared statistic and we get a p-value. Now the p-value is bigger than 0.05, so it's basically telling us there is not a significant difference. This treatment does not have an effect on the propensity to give, the probability of giving. But you'll probably find that if you had a larger sample, that would become significant. The problem here is power. I'm going to talk more about power later. The chi-squared test is not very powerful, and that's why we're not finding evidence here. Okay, the amount given. To look at the amount given, we're looking at the t-test. This is the independent samples t-test. The statter command is t-test by treatment. Here we're finding the two means. We've got the mean of giving with no communication, that's 13.8, and the mean of giving with communication, that's 24. As we said earlier, the t-test is based on that difference, that minus that difference, and then you divide by something in order to turn it into a t-statistic. The t-statistic is what you see there, minus 2.3. And again, we're interested in the p-value. The p-values are given at the bottom, and notice there are 3 p-values usually. There's a 2-tailed p-value, and there's a 1-tailed greater than p-value, and there's a 1-tailed less than p-value. Well, which one do you look at? It depends whether you have a prior belief. When we do this experiment, we have a prior belief that communication has a positive effect on giving. So we have a prior belief that that number is going to be bigger than that number. we have a prior belief that the difference is going to be negative, actually, because it's that minus that. So that's why we look at this p-value. We're looking at this alternative hypothesis. There's our p-value, 0.0121, significant. Okay, there is a significant difference between giving the amount given under communication and the amount given under no communication. There's the p-value. I hope everyone knows that if a p-value is less than 0.05, it's a significant effect. If the p-value is less than 0.01, then you can say it's strong. There's a strong effect. This is not a strong effect, but it's an effect. Now, when you do that t-test, you're assuming equal variances. In other words, we're assuming that the standard deviation of the data, or the variance of the data, is the same in the treatments. Well, it looks a bit like that one's bigger than that one. So we need to test the hypothesis that the variances are the same. That's the next test. To test the equality of the variances, it's SD test. We've got those two standard deviations. This is basically the same table as before with the means, but this time we're looking at the standard deviations. How do you test the equality of variances? You find that ratio. You find 20 divided by 40 or 14 divided by 20, and you square the ratio, and that gives an F statistic, which is here. And then again we have a p-value. Let's use the two-tailed p-value. What we've got is mild evidence. It's not quite evidence, because look, 0.051. We've got mild evidence that the variances are different. If the variances are different, then you have to do a t-test assuming unequal variances. So you use this option here, and it doesn't actually change the result in this situation. That's probably because we only had mild evidence of a difference. There's something very interesting here. The degrees of freedom for this test. When you've got unequal variances, the degrees of freedom for the test is not a whole number. Now, if you're interested in why that is, then look up the paper by Satterthwaite. It's from 1947. As I say, if you're interested, have a look at that paper. Testing for normality. I said earlier, when we looked at the histograms, we could see the data's not normal. How do we test formally for normality? You do a skewness kurtosis test. SK test is the static command. This tests for skewness. Skewness is asymmetry. A normal distribution is symmetric. So a normal distribution has skewness 0. If the skewness is positive or negative, then it's not normal. So here's a p-value for skewness. Here's a p-value for kurtosis. Well, skewness is the third moment of the distribution. Kurtosis is the fourth moment of the distribution. So kurtosis is the expectation of x to the power 4. Skewness is the expectation of x to the power 3. For the normal distribution, skewness is 0. Expectation of x cubed is 0. What is the expectation of x to the power 4? What is kurtosis for a normal distribution? Does anyone know that? Three. The answer is 3. The kurtosis of the normal distribution is 3. So there's a test being done here. Is the sample kurtosis equal to 3? Yes, it is. Actually, when there's no communication, we're accepting normality. Now, that's a bit of a strange result because we can see in the graph that it's not normal. The problem is, again, power. With only 30 observations, this test is not very powerful, meaning it's unable to detect a departure from normality. I'm going to come back to power is really important. I'm going to come back to it in a minute when we finish talking about all the tests. When we do this skewness kurtosis test for communication, we actually reject. We're accepting skewness. No, we're accepting the null of no skewness, but we're finding non-normal kurtosis. Know that these tests are done separately. There's also a joint test. The joint test is a chi-squared 2 because there are two things being tested, and that's the joint p-value. So for one of these, we're rejecting normality strongly. So what do you do if you reject normality? What do you do if your data's not normal? you use the Mann-Whitney test. The Mann-Whitney test is a non-parametric test. Now, what's the difference? When you do a t-test, you're actually looking at the values of all the numbers in your data set. When you do a Mann-Whitney test, you're not looking at the values anymore. You're ignoring the values, you're just looking at the ordering of the observations. You're just asking which observation is highest, which is second highest, which is third highest, and so on. You're ranking all the observations, and then you're asking the question, are the ones in the no communication treatment all at the top of the list? Or are the ones with the communication treatment all at the top of the list, and so on? So as I say, we're just looking at the ordering of the observations. We're just using ordinal information from the data. We're not using cardinal information, which is what is used in the t-test. So this is the Mann-Whitney test. It's non-parametric, and the advantage of this test is it does not assume normality. We're not assuming normality of the data. The cost of using this test is it's not going to be as powerful. Power keeps coming up. Because we're using less information, we're throwing away information, that is the cardinal information in the data, we've got a less powerful test. And we can see that here because that's the command, rank sum. It's looking at the ranks, it's summing the ranks for the two treatments, it's comparing the two rank sums, and it's obtaining a test statistic from that comparison and a p-value. The p-value is 0.04. So again, we've got evidence, but it's not as strong as before, because with the t-test we've got 0.012, now we've got 0.045. So this is a safer test to use, but it's less powerful, so you're less likely to find evidence of your treatment effect. Now, if you really want to use the t-test, but you're worried about normality, the normality assumption, then you use the bootstrap. Has anyone ever used the bootstrap? Why is it called the bootstrap? This is really interesting. While you think about that, I'll have some. Okay, why is it called the bootstrap? Because it's called the bootstrap because you're performing a test using only the information in the sample. You're not using anything else. So this is why it's non-parametric. You're not assuming anything from outside. You're just using the information in the sample. Just using the information in the sample is a bit like pulling yourself up with your bootstraps, right? Do you understand what I'm saying? Bootstraps, shoelaces. You try to pull yourself off the ground by your bootstraps. That is what we're doing when we do this test. Okay, bootstrapping the t-test. The bootstrap procedure consists of 5 steps. Apply the parametric test as we have already done, and you get a test statistic. Stage 2, generate a healthy number of bootstrap samples. These are samples of the same size as the original sample. They're drawn from the original sample, but they're drawn with replacement. Okay, this is what confuses people. How do you draw a sample from the original sample without it being the original sample? You draw a sample with replacement. That means when you draw an observation, you put it back before you draw the next one. So that's what bootstrap samples are. You generate lots and lots of bootstrap samples. You do the test for all of the bootstrap samples. This gives you a distribution of test statistics, and then you obtain the standard deviation. You obtain a new statistic, which is your original test statistic divided by the bootstrap standard deviation, and then this gives you a bootstrap p-value. When you do the bootstrap in Stata, the syntax is this. You've got a bootstrap command in which you specify the number of bootstrap samples you want, and then after the colon you write the command that you want to bootstrap. The command that you want to bootstrap is the test that you did earlier. When you do this, it's quite intriguing because you get a sequence of dots on the screen. Dot, 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 dots appearing on the screen. A dot appears when a bootstrap sample is drawn. So try this out. Try this out. It's fun. And then when you do this, you get a new result. You get a test statistic. Well, that's the original test statistic that you had. but we've got a different p-value. The p-value is now 0.027. Now, there's one problem with the bootstrap. I've told you that it's a way of dealing with, it's a way of avoiding the normality assumption because we're just using information in the data. So it doesn't matter if your data is not normal. The data can be any distribution the bootstrap weighs. There is one problem with the bootstrap, and that's that if you do it twice, look at that result, 0.027. If you do it again, exactly the same thing again, you get a different answer. Now, is it obvious why that is? You get a different answer because it's a random procedure. Bootstrap samples are random samples. So obviously, each time you use the bootstrap, you get a different answer. How do you deal with that problem? Any ideas? You use a lot of bootstrap samples. So instead of 99 there, we have 9999. You can make that number as high as you want. You can make it 1,000,000. Make that 1,000,000, press enter and go away and have a cup of coffee and come back. And then your p-value will be accurate. So that's the bootstrap. Then we can go further. We can test entire distributions. What we've been talking about so far is comparing the means of two treatments. And then, and that's the t-test. If you want to compare the medians of two treatments, I didn't say this before, comparing the medians is the Mann-Whitney test. Comparing the variances, we did that as well. So we've done all sorts of different tests. But what if you want to compare the entire distribution? What if you don't know if it's the mean that's changing or the median or the variance or something else? Then you test the entire distributions. So here's the CDF. The blue one is the CDF of no communication giving, and the red one is the CDF of communication giving. The fact that this one is below and to the right just means with communication, giving is higher. How do we know if the red one is significantly different from the blue one? The thing that we find here is the maximum vertical distance between the two. Where is the maximum distance? I think it might be here. There. That vertical distance is the test statistic. What's the name of this test? Does anyone know the name of this test? Great name. That test is the Kolmogorov-Smirnov test. Yeah, this is how you do it in Stata. K-Smirnov, Kolmogorov-Smirnov. Let's just go back to the picture. That is the test statistic. What is it? There's 0.6. That's 1. So it's about 0.3, 0.35, this distance. When you do the test in Stata, you get the test statistic there, 0.33, and the p-value there. So we have evidence. What's this one here? This is a one-sided test or a one-tailed test. On the other side, we have this test statistic. The 0.33 is the highest distance between the blue one and the red one. The second test is the highest distance between the red one and the blue one. Well, the red one is never above the blue one, and that's why the second test that you see here is 0. So this is the one we're interested in, 0.036. We have evidence that the two distributions are different. Now there's another test for comparing entire distributions, which I'm becoming more and more interested in because I'm finding it's very powerful. And this is the Epps singleton test. The command is ESCF test. That's a Stata command, although actually it's not a Stata command, it's a user-written command. So if you want to use this test, you have to install that command. And it's very easy to install. You just find it, you use the command find it, name of command, and then you press a button and the command is installed and then you can use it. And this is the Epps singleton test, and this gives us a stronger effect. 0.01 is the p-value. So Epps singleton is detecting the effect better than Kolmogorov-Smirnov. Okay, here's just a summary of the tests that we've been talking about. Chi-squared test did not give us a significant effect. T-test did. and it's almost strongly significant. Unequal variance is no difference. Mann-Whitney gave us an effect, but not as strong as the t-test, and that's because it's non-parametric. Bootstrap gave us not so strong as the t-test. Now the bootstrap, in a way, the bootstrap test is the one we should be looking at, because the bootstrap version is the one that does not assume normality. We're not confident about the normality assumption. Kolmogorov-Smirnov, significant, but not as strong as that. Epps-Singleton is as strong as the t-test. So those are the tests we've been talking about. The next thing is within subject tests. Now what we've been talking about so far is between subject tests. We've got 30 in no communication and 30 in communication, and we're comparing the means or the distributions or whatever between the two samples. Another way of doing this is to assume there are 30 subjects who have each been observed in both treatments. All right? Can you imagine what we're doing here? We've got 30, we haven't got 60 dictators anymore, we've only got 30. And we ask them to play the dictator game with no communication, and then half an hour later we ask the same people to play the dictator game with communication. And the best way of presenting the data is like this. This is no communication, communication, and the fact that most of the observations are above the 45-degree line tells us that giving is higher with communication than with no communication. How do we test that? It's a t-test again, but it's a paired comparison t-test. Paired comparison, it looks the same as before, but because it's a within subject test, we're getting a much stronger effect. The p-value that we can't quite see here is considerably less than 0.01. So we're getting strong significance. When we use a within subject test, we get strong significance. There's a non-parametric version of this test, which is a bit like the Mann-Whitney, but it's for within sample tests, within subject tests. Again, this is strongly significant. And there's a very non-parametric test called the sign test. Even with this very non-parametric test, we're getting strong significance. Okay, getting on to power analysis. Power analysis is becoming ever more important. This is the Journal of the Economic Science Association, issue 1. A necessary but not sufficient condition for publishing a replication study or null result will be the presentation of power calculations. In other words, to get a paper published, you have to do power calculations. That means when you do a test, you have to tell us how powerful it is. The power of a test is the probability of finding an effect when the effect truly exists. Okay? Is that simple? Power of a test is the probability of finding an effect if there is an effect. Technically, it's the probability of rejecting the null when the null is false. And a power analysis is used to find the power of a given test or to find the sample size required. This is probably more useful. It's used to find the sample size required to attain a given power, and the power we're looking for is usually 0.8. So this is the test we did earlier. It's the independent samples t-test. What is the power of this test? Remember, this is exactly what we saw earlier. We've got two means. We're comparing the two means. We've got a test statistic there and a p-value there. What is the power of this test? In other words, if we know that the means are that, and that standard deviations are that and that, then what is the probability of finding an effect? Well, this is a stata command. It's the power command in stata. And this is very easy to use. To use this command, you do not need data in memory. Okay? This is just like pressing a button on a calculator. You can go into stata and type this command. It will give you this answer. You don't need any data in order to do this command. Power command. We're saying what the means are. After the comma, we're saying what the sample sizes are. We're saying what the standard deviations are. And stata works out the power of the test to be 0.62. 0.62, that's the probability of finding an effect when these are what the means are. 0.62. Well, the benchmark for power is 0.8. You want your power to be 0.8. To get your paper published, your power should be 0.8. So the question we want to ask here is, what does the sample size need to be for us to have a power of 0.8? Well, we just have to change the power command a little bit. What sample size would be required for power 0.8? Now we write power to me, put the means down again, but we do not put the sample sizes. We just put the standard deviations and we put P 0.8 because that's for power. We want the power to be 0.8, and it works out that the total sample size is 92 and the number per group is 46. So what this is telling us is we shouldn't be using 30 subjects in each treatment. We should be using 46 subjects in each treatment. That's what the power analysis tells us. And then another really useful thing about the power command, this is one of the reasons I said you should be using Stata version 16, because some of these features are only available in version 16. If you add the option graph at the end of the power command, then you get what's called a power function, a graph of the power function. This is power against sample size. So when does it reach 0.8? 92. That's what we just worked out. But if we go on increasing the sample size, we can increase power all the way to 1. Notice power is a probability, so it can't be bigger than 1, and it can't be less than 0. You can do it the other way round. You can find the total sample size required to attain a power of this. The power is on the x-axis. To get a power of 0.8, we need 92. So those are very useful, those graphs. And then we can work out the power of the paired comparison t-test. This is for the within subject test, and we find that that's 0.6. That's very close to the power of the independent samples t-test. But that's assuming the correlation between the two treatments is 0. This is the graph again. The correlation between no communication and communication is actually 0.7. If we build that into the power command, then we get a much higher power of 0.99. If we then ask what does the sample size need to be, the sample size only needs to be 14. If we're doing within subject test, that is, if we're doing one of these tests where you ask the subjects both questions, then you only need 14 subjects in order to get a power of 0.8. Well, between subject versus within subject, there's a clear power advantage enjoyed by within subject test. This is important for you if you're going to do any sort of experiment and test a treatment. It's actually much better statistically, from a statistical point of view, it's better to have a set of subjects and to expose the subjects to both the treatments. You'll get a much stronger result. However, required sample is lower by at least 50%, even higher savings if there's a correlation between treatments. But within subject tests suffer from order effects. Like if you ask subject 2 questions, then getting them to think about the first question alters their behavior in the second question. This is what's called the order effect. And what you need here is a crossover design. So you need to ask half of your subjects the no communication question, and then half of first, and the other half of the subjects, they get the communication treatment first. The screen stopped working, but this is still working. changed again.
Yeah, sorry.
Oh yes, working again. Thank you. Shall I move it on here? Okay, well all of the power calculations that I've just shown you relate to the t-tests only. If you want to look at power of other tests, then you have to use Monte Carlo. That is, you have to use simulation. And I've done some Monte Carlo, which tells us that it depends on the distribution of the data. If your data is normally distributed, then the t-test has the highest power of all the tests. But if the data is not normally distributed, in particular if it's asymmetrically distributed, which most experimental data is, chi-squared is an asymmetric distribution, then funny things happen. The t-test is no longer the most powerful. The Epps-Singleton test becomes the most powerful test when the data is asymmetric. That's why I said I'm becoming very interested in the Epps-Singleton test. I'll just very briefly talk about structural models of giving. Now, all we've talked about so far is treatment tests, comparing means, comparing medians and so on. That's what's called reduced form analysis. If you want to do structural analysis, what you're doing is you're estimating the parameters of a utility function. So why don't we write down a model? X1 is own payoff, X2 is others payoff. Individuals have a utility function, looks like this. Now, when you learn first year economics, first year microeconomics, you have two goods, right? You have two goods, beer and pizza. What are the two goods that you have in the textbook? In the British textbook, I think it's beer and pizza. Anyway, it's the same thing, but the two goods here are own payoff and others payoff. Those are the two things that give you utility. And we want to estimate these parameters econometrically. The dictator's problem is this: maximize utility subject to the budget constraint and non-negativity constraints. So it's a bit like this. You've got an indifference map and you've got a budget constraint. And something about dictator games is, obviously there's an endowment. The dictator has an endowment, but you can vary the price of giving as well. You can change the price of giving. You can say, if you want to send $10 to player B, then player B receives $20. That's if the price of giving is a half. So there can be a price of giving different from one. So the slope of the budget line can change around. So with a give game, you've got a budget line, we've got an indifference map, and there we have an interior solution. So this dictator is giving a positive amount to the other player. This dictator here is giving 0 because they're a corner solution, right? 0 giving is corner solution. So the data looks like this. This is what the data looks like. This is 0 giving. This is positive giving. Now this is a scatter plot. When you do a scatter plot, very useful thing is jitter. Use the jitter option, because the jitter option moves points slightly, randomly. So you can see why jitter is important, because jitter makes it clear where the most observations are. Most observations are here, 0 giving. There are quite a lot of observations here. There are very few observations up here. So that's what jitter is telling us. Notice that the observations are all on straight lines. The straight lines are the different budget lines in the experimental design. So that's dictator game data. And then there's something called a take treatment, which is a different treatment in a dictator game. Instead of asking subjects, how much do you want to give? Instead of asking a dictator, how much do you want to give to the receiver? You ask the question, how much do you want to take from the receiver? How much do you want to take of their endowment? And this is the same thing again, same utility function, but here the budget constraint is here. You're asking them how much they want to take taking means we're down here. So again, this subject here is a corner solution, they don't take anything. This subject here is going to be an interior solution, they're going to take something. And the taking data looks like this. Most subjects, well, a lot of subjects take 0, but some subjects take quite a lot. And the question we're asking here is, if we estimate that utility function using the give data, and then estimate it using the take data, are the two utility functions the same? They should be. In theory, they should be the same, but they're not. Changing the experiment from a give game to a take game seems to change the utility function, and this is the finding of this research. And it's summarized here. This is the estimate, posterior estimate of the sort of altruism parameter. In a give game, this is the distribution of it. In a take game, it moves a long way to the right. So this is just another way of looking at the effect of a treatment, and it's what we might call a structural treatment test. Okay, completely changing the subject, I want to show you a page on scholarships for Thai students. The School of Economics at the University of East Anglia is in constructive discussions with Thammasat University. Please, say this word. With these 3 universities, and the reason why we're in discussions with these 3 universities, we've heard they are the top universities in Bangkok or in Thailand. That's why we're talking to these universities. We offer 2 international scholarships equal to 50% of international fees to academically outstanding applicants who have received an offer on one of the MSc programs. I'll talk about the MSc programs in a minute. What's the 50% international fees? Well, the fees are currently £16,400, which I believe is 620,000 Thai baht, which means that the scholarship is half of that. So the scholarship is 310,000 Thai baht. Okay? Does that give an idea of what this scholarship is? 50%, is this correct? What?
17,250. Of the prices so the tuition fee, 17,215.
Sorry, I thought someone said yesterday 16 for
17,215.
Okay, I'm sorry. Add a little bit to these numbers. They're not far out. The deadline for applications is 15th of March 2020. So you've got a bit of time to think about this. What are the MSCs in economics? You can choose a wide range of MSc degrees divided into 2 programs. Now, is everyone in this room doing an economics degree? Or is anyone doing a degree other than economics? The students in the room, that is. You're all doing economics. You're all economics students. Okay, if you're doing an economics BSc or an economics first degree, then you're interested in the academic and professional program. The degrees in this program are MSc in economics, MSc in behavioural and experimental economics. That's what I've been talking about in the presentation. MSc in competition economics and policy, MSc in finance and economics. You can do one of these 4 if you already have a degree in economics. The entry requirement is a good degree in economics. And the MSc in economics looks like this. You have 3 modules in the autumn semester, 3 modules in the spring semester, and then you have a dissertation in which you're working on a topic of your own choice, supported by a dissertation supervisor. And then the applied training program, that's the program for students who do not have a degree in economics, but I'm not going to talk about that one. Here we have a page with basically all of the options that can be taken. This is a complete list of all the options that you can take as part of your MSc in economics. There's space in the program for options. So whatever your interest is will determine what you choose from this list. And this is where we are. This is a map of the UK. London is here. Norwich is here, so we're not too far from London. But because we're in Norwich, it's nice. It's a small city, smallish city, not too small, not too large, and it's far enough away from London without being too far away. And you can get to Norwich easily by air because you fly from Bangkok to Amsterdam, and then from Amsterdam to Norwich. There is a nice airport in Norwich. This is a picture of UEA. UEA from the air, the University of East Anglia. We're about 2 miles outside the centre of Norwich. As you can see, we're in very pleasant surroundings. Good facilities. Whatever your non-academic interests are, they're probably covered at UEA. This is Norwich, nice old city, and we're not too far from the seaside. Okay, thank you. Thank you for your time.
Just in case if anyone has a question to ask, or any other issues that you want to ask also related to University of East Anglia, right?
I'd like to ask about the personnel involved in this project. Is there any of the mathematical economics expert or mathematics expert involved in the project you are doing?
Sorry, in which project?
The project in your textbook, in the
Experimetrics. So you're asking in the project, the general project, experimetrics.
In the latter part of the
No, when I was talking about structural models.
Yes, there are some of the mathematical models.
Well, I mean, I'm working with an ex-PhD student, and their PhD involved the experiment. They collected the data in their PhD, and I'm still working with them, and I'm doing the programming and the econometrics.
So are there is there a field of expertise? Actually, mathematical economics.
Yes, yes, mathematical economics is quite important there because obviously the economic concept, the Kuhn-Tucker conditions are being used to find the optimum of utility functions subject to budget constraint and non-negativity constraint. Is that what you're interested in? Yes, it is a mathematical economics problem. And if you're interested in it, then talk to me about it.
Maybe I just ask some question regarding like the currently popularity of doing a lot of experiments like in the field research, right? And then what do you think about in terms of how in the research fields of doing experiment in terms of getting the participants using students? Like a lot of time when we do experiment, right? Most of the participants that if we are going to do the experimental lab, we need to normally we need to either hire or ask students to come in participants. Whether in some cases or in some experiments, the payment has to be in kind of like part of the experiment. In some experiment, there is no payment. What do you think in terms of like doing in the real, closer to the real payment, or like using the money as one of the incentives, comparing to just like doing kind of like hypothetical questions, or just use what we call kind of like altruism in terms of like coming to participate.
I think this question is about the importance of incentives in experiments.
Yeah.
How important is it to give subjects real prizes, real money prizes? How important is it to provide incentives to participate in experiments and to make effort in experiments? Well, it's quite interesting actually because economists experimental economics, the experimental economics profession has always thought it's very important. It's essential. And someone's recently done a meta-study on incentives, and they found that all the papers that are published in the American Economic Review using experiments have incentives, have money incentives, task-related incentives. That means it's no good just paying subjects a show-up fee. Here's $20 for your time. That's no good. You have to have task-related incentives. You have to have a way of saying, we gave incentives to subjects for trying hard, participating hard in this experiment. So the economics profession thinks it's very important to have incentives, task-related incentives. But psychologists also do experiments, and they do not think incentives are important. So this is one of the aspects of disagreement between economics and psychology, incentives. Some economists think that we're taking it too seriously. It's not that important to have task-related incentives. We can rely on subjects, altruism, good word to use. Altruism in the sense of they want to come and take part in a research project. And sometimes you find that incentives are counterproductive. So I think what you've got to look at is you've got to look at the application. You've got to ask, if I'm doing this experiment on this application, how important are incentives in this situation? I think that's the question we have to ask. Sometimes they're more important than others. There's an interesting thing, I just mentioned the difference between economics and psychology. Another thing we're very strict about in experimental economics is you're not allowed to deceive subjects. That is, you're not allowed to lie to subjects. You're not allowed to tell them something that's not true. Now, why is that? Why are we very strict about that? It's because we have a pool of subjects that we ask to come back several times to experiments. If you lie to them once, if you deceive them once, then they will expect to be deceived the next time, and that will change their behaviour. They'll just be saying, "Oh, what does he mean when he says that?" So that's why we never deceive subjects. Psychologists think that it's perfectly acceptable to deceive subjects. And it's a standard part of psychology experiments to deceive subjects. There are very good examples of that. I think that's another interesting contrast between the two disciplines, economics and psychology. But yes, I think the standard is to offer twice the minimum wage. Do you have a minimum wage here in Thailand? What's the minimum wage?
Like 300 baht per day. Wow, what?
300 per day? What's that per hour? 50.
8 hours.
40 per hour. And there are a lot of people on the minimum wage. Is it a binding constraint? Do a lot of people earn the minimum wage?
A lot of people are home.
But is anyone at the? Yes, there must be people. Okay, I think the standard we have, the minimum wage is around £7 an hour. So in an experiment, students can expect, on average, students should receive £14 per hour that they spend in the lab. On average. I mean, some students who do better earn much more than that. Students who do worse earn less, but the expectation is twice the minimum wage. Do you have an experimental lab here?
Not yet.
Do you teach behavioural economics?
I'm not teaching, but
No, I mean, does
exactly.
your team?
Yeah, but there are courses in behavioural economics.
Good. Is anyone studying behavioural economics? So everything I said is new.
Excuse me, please.
Okay, to the microphone.
I have one question because I'm curious about behavioral economics. although I have no idea at all about experimental laboratory or whatever so called. But one thing I have to mention that, like you said earlier, apart from the interaction between psychology and economics, behavioral economics, do you usually use any kind of test to do or to think about ex ante or ex post perspective before imposing tax policies, law, things like that in your country or in your experience?
So we're talking about policy here. Tax policy, did you say? Do we use insights from behavioural economics? Is that what you're asking?
Yeah.
Do we use insights from behavioural economics in the design of tax policies?
Or any case you just mentioned in your presentation. For example, dictator game, t-test, man winning test. Do you use them for imposing some policies?
Of course. Yes, I mean, if you are designing a policy and this policy will work given a certain behavioural fact, then you need to establish this behavioural fact using exactly the types of tests that I've been talking about. So yes, you'd have to test a treatment and you'd have to have evidence or strong evidence of the treatment effect before you used it in policy design.
And was it conducted by only economists or you work in collaboration with others?
Well, like I say, economics, behavioural economics is halfway between economics and psychology. There is a lot of collaboration between economists and psychologists for this reason. Especially since, come back to the differences. Economists have traditionally been interested in decisions. Economists just look at the decision that's made. The jobs that people do, how many hours they work, the mode of transport they use to get to work, the decisions people make. Psychologists are interested in much more than that. I'm an economist, I shouldn't be saying this, but I'm saying psychologists are, in a sense, they're much more interesting than us because they don't just look at the decisions, they look at the process leading to the decision. I'll just give one example. Psychologists have got very interested in something called eye tracking. Does anyone know what eye tracking is? That's if you use equipment, you've got someone in front of a computer and they're looking at different products on a screen and you want to know which one they're going to choose. You look at their eye movements. You want to know what they're looking at and how long they're looking at each thing. Because if you know what their eye movements are, then that's a very good predictor of what they're going to choose. So that's an example of how psychologists are not only interested in the decision, they're interested in the process leading to the decision. So, as I say, psychologists and economists have got complementary skills, and it's very useful bringing them together.
Thank you.
Thank you.
Talk into the microphone.
Okay, actually, I think your explanation is interesting because, I think after I've studied some economic theories course, say microeconomics and macroeconomics and theories, I think the courses is I think the content of the course is concerning about the logics and processes of the, say, something like the price aspect in microeconomics or perhaps the say something like ISRM model in macroeconomics as well. I think it's concerning about the process as well. I don't think it is not very concerned about the decision made.
You're saying this is all relevant to macroeconomics as
Yes,
well?
it's relevant to the, say, the economic theories, but perhaps it may be the main concern of the behavioral economics studies.
That's right. Well, it's interesting you mentioned macro. If you're a macroeconomist, then have a look at the experimental economics literature because people are doing macro experiments as well. I won't tell you about them, but there are macroeconomic. What I've been talking about is definitely micro, isn't it? It's an individual decision, utility function, and so on. But there are macroeconomic experiments too done in labs. So yes, and I agree. Process of decision making is becoming more and more important. I mean, economists are being lured into doing things like eye tracking. Because we're becoming more interested in the process. Another thing you can look at is decision time. How long does it take a subject to make a decision? Is it very quick, 2 seconds, or is it 25 seconds? That's very important. How long do they spend thinking about this? And if they make a very quick decision, is it because they understand it well, or is it just because they're not interested and they're choosing randomly? These are very important questions. Say it again?
To make decisions, it depends the individual behavior on their, some people make decisions very quick. It's not based on your personality and your behaviors. So,
well, is it not to do with thought process, speed of thinking?
Yeah,
But it could be just they're not interested. They're just choosing randomly, or it could be they're very quick. They've worked it out quicker than everyone else. So you need to be careful there.
Okay, thank you very much for your presentation. I'm now teaching economics of climate change, and I think they have a lot of implication about the behavioral economics and implication in environmental fields and also for climate change policy like that. So first, I would like to know that, for example, like if in environmental terms, if we say that like people will not tend to pay or sacrifice some of their money to conserve the environment or to clean up the environment. Just and you show some result that one factor is that because they realize that it's their earned money, it's their earned income. How to make that like very significant in lab design that the people will realize that this is their own money, because like when we have like the carbon tax, environmental tax, people have to pay their real money, and how to decide it in the lab.
I think there are two things there. You're asking a question about when the recipient is, we're talking about climate change here. People are paying money to reduce climate change, essentially. So a lot of people have a strong intrinsic motivation to reduce global warming, reduce greenhouse gas emissions and so on. So that's one thing. I think people are more likely to want to contribute when that is the outcome than if they're just giving to someone else. Now, you also mentioned this problem of earned income. Well, you can't ask people to come to an experiment and use their own money, the money that's in their pocket. You can't do that. It doesn't get past the ethics committee. When you apply to run an experiment, you have to get past an ethics committee. So, if you said you were going to ask people to bring their own money to the experiment, you use their own money, no, you can't do that. You have to give them money at the start of the experiment, or you make them work. This is the key. Earned income in an experimental setting is they're carrying out a typing task or something. They're copying some text. And the more text that they copy correctly, the more money they earn, and that's how they earn their endowment. That's how we deal with the earned income treatment. I mean, does that answer your question? I think there were two things there. You're asking about the environment, you're asking about earned income.
And is that for the first question, does it mean that it is probably that when like the lab design is about the theme is environment or climate change, something like that, we have the effect that you said, like the experimental effects that the people, we know that this lab is about like something environmental, they should sacrifice something, otherwise they will be...
Oh, you're asking, is there an experimental demand effect?
Yes.
Just because you're mentioning the environment, people think, oh, well, I'll have to give more money. No, I thought you meant you're doing an experiment where the money that's given by the subject actually goes to some environmental cause. That's possible. That's done sometimes. You get subjects in a lab, you say, I want you to think about how much you're going to give to this cause. And it might be an environmental cause, it might be helping homeless people or helping a food bank, or it's a charity of some sort. And the money really goes to that charity. It's not hypothetical. I think it's better if it's real, a real outcome. And yes, people are more willing to give if there's a real outcome like that, and if the recipients are deserving.
Any other questions? We get some quite different questions.
It's about the UPA's MSc program. Could the MSc student at UEA read the PhD level non-economic courses, say mathematics, statistics, or psychology courses? Could the MSc student at UEA read the PhD level courses and the non-economic PhD level courses, say mathematics, PhD level courses, like that?
Are you asking if MSc students are allowed to take PhD courses?
Yes.
Well, they're probably allowed to. They're probably allowed to attend PhD course, but they've got enough to do. You know, if you're doing a master's degree, you've got enough in the way of taught modules and your dissertation. You don't really want to be doing extra things. You could do it if you wanted to.
Very intensive. Okay, I guess that's probably all. And so today we have to say very thank you for your talk and then introducing behavioral economics. I mean, we have class on this, but maybe a lot of students hasn't yet enrolled in that course. So this is going to be giving some more short introductions to some of the concepts in behavioral economics, right? And also how we use statistics or a little bit related to econometrics.
Experimetrics.
Yeah, experimetrics, yeah. All right, and then introducing University of East Anglia as well, all right? So thank you so much for coming and give a talk for us today. All right, thank you so much.